Hello and welcome to Veterinary Epidemiology. One of the major tasks of epidemiologists is to measure the frequency and burden of diseases, and they do so by employing measures of disease frequency. The approach followed to derive to these measures is starting by counting the number of cases of a certain disease or health events and describing them into the classical triad of place, time, and animal type. And then divide the cases by an appropriate denominator to calculate specific rates, and then compare those rates with different groups of animals and to different locations. So the counts are simple enumeration of number of cases of a disease into a given population, and they are very, very important because through counting cases we make the epidemic curves, and the epidemic curves are number of cases in time. So numbers of cases per se are limited information, but if connected to time or to the specific populations where they are derived from, they make sense. So it's most important not to lose count. The types of measures that can be derived are ratios, proportions, and rates. And all three of them are basically a fraction which is composed by a numerator, a denominator, and a multiplier. So the counts, we said, must be put into the context based on the population which they arose, and then this can be created into rates or ratios or proportions that could be also implemented in a period of time. So the numerator and denominator can be summed up with the multiplier, which, depending by the measure, it's making more sense, and it's normalizing, let's say, the measure itself. But we'll see the use of the multiplier based on specific measures in future when we'll talk about incidences, prevalences. The difference between the three measures we are talking today is that the ratio has mutually exclusive the numerator and the denominator. For example, we have the affected and the unaffected animals. So for a ratio, there would be always two-sided, and they are exclusive to each other, so either the affected or the unaffected. Into a proportion, the denominator comprises within itself the numerator. So we would have the affected over the affected plus the non-affected. So the numerator per se, it's a subsection of the denominator. When we talk about rate, there is also the time component, and the time component is very important here because it's a proportion in itself, but involves time. So in the denominator we include the different times, and we will see how we include time into that. So let's see a bit what are these differences, and let's take an example of 5 puppies, which from them 2 are females and 3 are males. If we compare part to part, females to males from the puppies, we would say that the ratio of males to females is 2 to 3, or the vice versa, 3 to 2, if females to males. When we talk about a proportion, then we say a part to the whole population of puppies, which is males to all puppies, it's 2 to 5, and to female to all of puppies, it's 3 to 5. So technically it's a ratio, but it's proportional. If we specify, for example, that the population is not all puppies, but all the dogs, all the family dog, would have the father and the mother, then the population definition changes. So I'm letting that to you to do the math out of that. So a ratio shows a relationship between two mutually exclusive groups, and it's calculated as a relative magnitude of two quantities or a comparison between the two values. So the calculation is a number or a rate of a disease or events or animals or whatever thing countable in one group above a number or a rate or an animal in another group. It's a fraction between these two. Properties of a ratio are that they are commonly used both as a descriptive measure and as an analytical tools. As descriptive measures, they can be used like to say a comparison between male to females, like we said with the puppies. But as analytical tools, the ratios could be to calculate occurrence of a disease or mortalities or morbidities and convert them into risks, odds, etc., which are used to compare different groups. And the values of both the numerator and denominator can be divided by either the denominator or by the numerator. The values of both numerator and denominator can be divided by the value of the numerator or the denominator. So it's like we simplify the fractions that we divide or sum them up by a specific number, both of them. And then by applying either one or the other, we could achieve that either one becomes equal to 1 or the denominator becomes equal to 1. And that simplifies the fraction. The ratios have also the numerator and denominator that can be related or unrelated. So it's, let's say, as a numerator we could have apples above apples, but we could have apples above oranges. So that's an unrelated ratio, for example. Within the same variable, we could have two different categories, and then we could find the ratio between the categories of the same variable. In a research study, it was shown that a higher adult to young ratio decreases the aggressiveness among young horses. That means that more adult male horses there are for each of the young horses, the better they all get along, so they don't get aggressive. The ratio between the two categories of horses is for the same group, but with different category. Let's say because a horse either is young or either is an adult. It's within the same group, and that's the concept. If we see, let's say, a ratio for two totally different variables, and we take into consideration a country which has, let's say, 4 million cattle and 500 private veterinary practitioners, and then we do the math and we could end up with a ratio which says 0.00125 vets per cattle, and that's mathematics, but that's a bit difficult in expressing it. So to make it more understandable, we go back to one of the properties that the ratios had and we do a simplification. And to make it more understandable, we put the multiplier into the math. So let's say from the multiplier at 10 at power of 0, which is 1, we say the multiplier is 10,000, so it's 10 at power of 4. And then we get 1.225 vets per 10,000 cattle, which is a little bit better than before. But we could even do better than if we divide both the numerator and the denominator by 1.25, we get 1 vet per every 8,000 cattle, and that's much more better in terms of making more understandable the ratio we have. We could simplify the ratios to more understandable and getting more meaning, but we could use them either within the same variable with two different categories or more, or we could use them for two totally different variables. One of the measures which often is used in terms of ratios is death to case ratio, or what's became more known during these COVIDian times, the case fatality ratio, which is the number of deaths attributed to the particular disease and divided by the number of new cases of that disease for the same period of time. Basically, what it tells is just how much and how severe is the illness or the disease. So let's take an example. For example, rabies, which is a fatal disease at 100% if you develop clinical science, so it would have a case fatality ratio of 1. But another disease, let's say common cold, which by the way it's also related, it's a coronavirus, but it's not like COVID-2, have a case fatality ratio near to 0. So that's also used to compare different diseases, and that's very important as a number. But let's make an example, let's say, of death to case ratio. In a country, during a year, there have been around 15,000 new cases and 800 deaths because of tuberculosis. So dividing both the numerator and denominator by the numerator, we get a ratio of 1 death per 19 new cases. And if we do the reverse, let's say dividing both the numerator and denominator by the denominator and then multiplying them by 100, we get 5.3 deaths per 100 new cases, which means both options are valid and both options are correct to be used. So whichever it's suited better in terms of communicating the information. We have to note that presumably many of those which died had initially contracted tuberculosis years before, because this is a chronic disease. And therefore, many of the 800 cases in the numerator are not among the 15,000 in the denominator. So the death to case ratio, it's a ratio, but it's not a proportion. So keep this in mind in order to differentiate between the measures. So we go to the proportions now, and proportions compare a subgroup within the whole group. And they are usually derived into decimals, fractions, or percentages. That's how we express them. And the way to calculate them is that, for example, number of animals or health events with a particular characteristic or a specific disease on top of a total number of animals or events of which the numerator is a subset. So let's say the number of affected above the number of affected plus the number of unaffected per the multiplier of choice, of course. So the properties of proportions is that mainly they are used for descriptive studies, and let's say can describe the amount of a disease that can be attributed to a specific exposure, or convert it easily to ratios and vice versa, because they are interrelated, and as we said, proportions themselves are ratios, but we could convert them back. And then, as we said, the crucial distinction is that in a proportion the numerator must be included into the denominator, so it's always a subset of the denominator. Let's take an example of a proportion. For a farmer which has 2 sick cattle, and in total he has only 2 cattle, the sickness would affect 100% of the cattle. So that means it's a lot. But for a herd which has 50 cattle, they would represent only 4% of the cattle. So it's less. So proportions are used to show the burden of a disease, but it's of a paramount importance to report the percentage derived by the proportion together with the population, because 100% and 4%, it's still 2 cattle but makes totally different meaning for two different populations. So it's always to be clear what the population is used when we calculate the percentage, so the percentage would take meaning. One of the measures which we encounter quite often in epidemiology is the proportionate mortality. And it's the proportion of deaths in a specified population during a specific time and attributed to different causes of death, let's say, of mortality. And each cause is expressed as a percentage, and the sum of all causes is 100%. These proportions are not rates because the denominator of all deaths is not the size of the population in which the disease did occur. So to make it more clear, we take an example which was hugely broadcasted about the mortality of humans by which type of animals, and we see, that the mosquitoes are the most deadly one, accounting for almost 90% of deaths. So of proportionate mortality of humans, the top list is the mosquitoes. We arrive to the rates, and a rate is a measure of a frequency of an event which occur into a defined population during a specific period of time. And time is the very crucial point for a rate because the denominator of a rate has the time component attached to it, and that's which makes the difference between the other measures. And they are very useful in comparing disease frequencies in different locations, in different populations, and in populations with different sizes of them, being like the proportions, but they, as we said, include the time each of the individuals is at risk. But still, this is not clear, and there is a controversial opinion between epidemiologists, and some of them restrict the term of rate to measures that express themselves per unit of time. It's like a speed concept attached to it. So let's say when you drive a car, it's the speedometer says 100 kilometers per hour. So it has the time component and shows you the speed of a progression, for example, of a disease. It would be per year, it would be per day, it would be different time measurement, which shows the speed of the disease propagating into a population. While other epidemiologists use the term rate more loosely and refer to proportions with the case counts in numerator and the population denominator as rates. And these are basically the attack rates, but technically speaking, those are proportions. So it's a matter of controversy between different groups of epidemiologists, but we will stick with the group which says that a rate must have a time component. To make an example, let's say into a communal pasture where animals go for a couple of days, so those kind of pastures which are nearby the villages, and different villagers group the flocks together and put them into daily transhumance or weekly transhumances. And so we have at this communal pasture 2 sheep staying for 1 week, 3 sheep staying for 5 days, and 1 sheep stay only for 2 days. So that's the group of sheep we have in the pasture. And if one of them, during the pasture, one of them develops enterotoxemia, so basing ourselves on what we learned about the measures of frequency, we would say, well, it's 1 out of 6 sheep, which is 16 in proportion, it's 16.7 of them develop the disease of enterotoxemia. But, when we said, however, that each sheep had a different risk of developing the disease because they was there in the pasture for different periods of time, which means that they got exposed to the pathogen differently, so not in the same time, and so they had different exposure levels. So how we cope with that? Let's see it. So to account for this different length of time of exposure to the Clostridius, we calculate the sheep day, which is used for each day that the sheep stayed at the pasture. So we said that we had two sheep which contribute by 7 days each. So let's say 2 by 7, we have 14 sheep days. And then we had 3 sheep by contributing 5 days each, so we have 15 sheep day. And then we have 1 sheep which stayed only 2 days in the pasture, which contributes to the total amount of sheep days, 2 sheep days. So in total we have 31 sheep days. And then the rate of enterotoxemia in this pasture would be 1 sick sheep per 31 sheep days, which this is also an incidence. But we will talk more on the specific measures of disease frequency like incidences, prevalences, odds and risks, and other rates onto the next part of this lecture. Till then, be safe and see you next time.